One of the most interesting debates in the programming world is sorting algorithms. You've probably either heard about it or even implemented it yourself. In game development projects, you might not use sorting often, but there are times it's necessary, like sorting scores on a leaderboard, organizing an inventory, or managing specific needs depending on your project. For example, in one of my older projects, I wanted items to be neatly stored in the storage building. Or, when working with AI for bots, I wanted a sorted queue of requests so that the bots could process them quickly. So whether you'll need a sorting algorithm in the future, or you've already implemented one and, like me, accidentally unleashed the worst performing one possible, let's dive in and see if we can actually find the best sorting algorithm in Blueprint. In this video, we'll go over different types of sorting algorithms and find out which one is the best option. And by the end, we'll wrap it all up by turning it into a clean macro that will make sorting as easy as possible. Before we get started, you might wonder, doesn't Unreal Engine already have a built-in sort function? Why bother? And you'd be right, this function does exist in the newer versions of Unreal, and back then, we didn't have that luxury. So definitely use it where possible, as it's optimized for the best performance. However, this built-in function is actually limited when it comes to sorting keys within objects or structures, which is what we usually need. Here, as you can see, I tried sorting using a map, and while this works well in some cases, it falls short if we have two elements with identical keys. While there may be other ways to tackle this, it makes things more complex and often compromises the efficiency of our function, which can mean that the built-in Unreal sort doesn't quite meet our needs here. And beyond all that, it's at least a fun experience. Plus, in the end, you can always switch to C++ if you need serious speed, as it performs sorting much faster than blueprints. I won't cover every sorting algorithm out there. If you're interested in the full comparison, there are some amazing videos that go over all of them. For this video though, I'll be focusing on just a few key algorithms. I also used Int64 here just for testing purposes, for now. Later we'll get to a more general, versatile method that works for everything. For all these algorithms, I did my best to achieve the most optimized results possible. Let's start with the simplest algorithm, bubble sort. As you can see, this algorithm is really straightforward. We have a for loop node that repeats each time, and since we're pushing the largest element to the end with each pass, we reduce the loop by 1 each time until we reach the first element. At each step, if an element is greater than the previous one, we swap them. Next up is selection sort. This is probably one of the most logical sorting approaches that comes to mind for beginners, selecting the best or smallest element and placing it in the correct spot. Here, we go through each element from the first to the last, find the index of the best element, and swap it with the first index. Then we loop again, but this time starting from the next element in line. Next up is insertion sort. In the first loop, we start comparing from the second element. If the current element meets the comparison condition, for example, being larger than the previous, we keep checking the previous indices until we find the correct spot for it. Finally, we insert the element in its appropriate position. Since the element still exists in its original position and has now moved one slot forward, we then delete the duplicate to clean things up. One thing to note in Blueprint is that we're tapping into the power of C++ behind the scenes. As a result, some operations can be strangely efficient, like the insert function, which happens effortlessly here, even though it should be more costly. Next up is quicksort. This is where we start using recursive functions. In this algorithm, we take the last element as the pivot and compare everything to it. Although it might look simple at first glance, it's actually more complex than the previous ones. We start with a center index that represents the midpoint of the array. If an element is greater than the pivot, we swap it with the center index, building two sections around the center, one with smaller elements and one with larger ones. Finally, we place the pivot at the center index. Then we repeat the same process for the smaller and larger ranges, and eventually, the entire array gets sorted. I also created another variant of quicksort that uses two helper arrays. The approach is similar to the previous one. We fill one array with elements smaller than the pivot and the other with elements greater than the pivot. Then we recursively call the function for each of these arrays. For arrays with just 2 elements, I added a simple swap to make things more efficient. Finally, after sorting each of the smaller arrays, we append them together and rebuild the target array with the sorted elements. Next up is merge sort. As you can see, this is definitely our most complex algorithm so far. At the start, similar to quicksort, we just swap elements if the array has only 2 items. Then, we divide the array into 2 halves. The way we divide it might seem a bit unusual, but it's fast. Once we have the left and right arrays, we sort them recursively. After sorting, we merge them back together. In the end, whichever side finishes first will just fill in the rest of its elements with the other array's remaining items. And that's it. It's as complex as it sounds. So, these are all the algorithms I've created. Now, let's test the performance of each one. Here, I'm creating a large array and calling each of them in the event tick. However, each time, I'll increase the size of the array linearly. For comparison, I've also included Unreal's own built-in sort function so we can see how much slower our algorithms are in comparison. As you can see, the algorithms are ranked like this. It's pretty much what I expected. For the linear sorting algorithms, the cost has grown exponentially in terms of big O notation, but for merge sort and quick sort, the performance is much better. Look at the huge difference. Here you can also see the comparison between the two variants of quicksort. Contrary to what you might think, using the help arrays actually made the algorithm run slightly faster. And this is all the results we could have gotten.
Olet nyt terve.
Yes, if you pay attention, we can actually do much better. For insertion sort, as the first loop progresses, the array up to that point is already sorted since we've been placing each element in its correct position. This enables us to replace the linear search with a binary search to find the appropriate position more efficiently. Here's how it works. We define a ceiling and a floor, and repeatedly compare the middle element to the target element. If the middle is greater, we set the ceiling equal to the middle. If it's smaller, we set the floor equal to the middle. This continues until the ceiling and floor meet, pinpointing the correct position. Additionally, I created a different variant of this method, and you'll see why it made such a significant improvement. Now let's dive into the updated results. I've excluded bubble sort and selection sort, as we already know that performance wasn't worth focusing on, except for insertion sort, where we can really highlight the progress. Just look at the dramatic improvement in binary insertion sort. Incorporating binary search has made it far more efficient. In the original binary insertion sort, we were performing removal operations from the middle of the array, which significantly increased the cost of those operations. In the variants I prepared, I optimized the process by comparing and removing elements from the end of the array instead. This adjustment led us to achieve our best algorithm yet. The result, even better than quicksort. It also scales beautifully with array size, maintaining a growth pattern consistent with n log n. So we found our best algorithm. And luckily, it's not recursive, because creating a general-purpose method for recursive algorithms would have been almost impossible. What a relief. Now take a closer look at the function. Our entire process revolves around working with indices except for the point where a comparison is required. For the comparison itself, we can delegate this operation externally and simply take the result as an input. It might sound a bit unconventional, but it works beautifully. And here's the result. I think this might be one of the most complex macros you've ever seen. To achieve this, I had to use local variable nodes instead of regular function variables to store the indices. The rest of the functionality can work seamlessly with wildcards. For the output, we provide 2 pins for the elements being compared so the user can handle the comparison logic. We then take a Boolean input as the result of the comparison. I also added an execution pin for cases where the comparison logic needs more processing, though I hope it's used sparingly because it gets called frequently and could impact performance. Now, see how simple it is to use this macro. You just pass the array into the macro and define your custom comparison logic using the provided pins. For instance, decide whether to compare elements as greater or smaller and return the result to the comparison input. That's it, easy as pie. Let's move on to a few real-world use cases. Sorting the structure. For example, I created a structure and now I can compare any of its internal elements and sort the array based on that specific field. Sorting actors by distance. Here, I have an array of actors and I want to sort them by their distance from the player character. I simply calculate their distances and compare them. This is the result. It works perfectly. Sorting widgets in a panel. In this example, I have several widgets inside a panel. I can fetch them into an array, sort them based on a key of my choice like their names, positions, or any custom property, and then re-add them as children of the panel in the sorted order. It's versatile, efficient, and gives you full control over your sorting logic. I've prepared these nodes for you in a macro library that you can easily add to your project and start using right away. I've also included the for each loop nodes that I explained in the previous video. There's one more feature in this library that I'll cover in the next video, so stay tuned for that. Thank you so much for watching.